We've all seen it in the movies. One small crack in a spacecraft's hull or window, the air screams, and an ill-fated individual is squeezed through the hole and out into the void of space as some sort of meat slurry. If it's an airlock, forget it. Everyone in the vicinity is getting blasted into space like champagne corks. But would any of this really happen? Let's explore the physics of this classic movie trope and the time it happened for real on the ISS.
I'm Stu, and welcome to Debunked.
So, you're going about your average working day when suddenly the protagonist of your particular narrative bursts in being chased by generic space soldiers who discharge their weapons with the accuracy of a headless stormtrooper. One of the stray projectiles pierces the hull. What happens? Despite what you see in science fiction movies, this is far from factual physics.
To get a real understanding of the fluid dynamics at play here, we need to explain how decompression works.
First, what do we mean by a pressurized cabin? Here on the Earth's surface, we humans, and all other terrestrial organisms while we're at it, are used to the atmosphere bearing down on us, thanks to gravity's pull. What we're talking about here is the actual cumulative weight of the air molecules, from the edge of the atmosphere all the way down to the Earth's surface. Weight is a force, and the force acting on each unit of area is what we call pressure. For convenience, we use a unit of pressure called atmospheres, where the pressure at sea level is equal to 1 atmosphere, about 14.7 pounds per square inch, or 101,325 pascals. Nope, not that guy. It's important to note that while the weight of the air is acting downwards, at any given height, the pressure pushes in all directions, left, right, up, down, etc. Because our bodies have evolved to function under these conditions, very low or very high pressure scenarios are, shall we say, not conducive to survival. To ensure that our lungs, eyes, and the water in our tissues all continue to behave as normal, we can pump air into the cabin of a spacecraft until the internal pressure equals roughly 1 atmosphere. When we do this, we say the cabin is pressurized. In contrast to conditions at the Earth's surface or inside a pressurized cabin, the vast majority of outer space is a vacuum.
This means it's almost totally devoid of matter, and no matter means no pressure.
What we're dealing with then is a scenario in which we have a cabin filled with air at pressure of roughly 1 atmosphere set against the background of the vast coldness of space, which is pretty damn close to 0 atmospheres. So, what happens if we breach the hull so that there's a hole in the barrier between the 1 atmosphere conditions and the 0 atmosphere conditions? But before we find out the true physics of this scenario, we are meticulous about cutting through all the noise of myths and misconceptions to present you with fact-based content. That's why we're working with today's sponsor, Straight Arrow News, because they apply this same approach to journalism, helping you uncover media bias, so you can see how every side of the political spectrum reports on a story. In a pretty polarized world, it's really important to consume current affairs in an unbiased way, so that you're not steered in one direction or another. SAN delivers you the baseline of what the news is, the facts, clear, direct, and unbiased, and from there you can dive deeper into the news that's important to you, allowing you to make a decision on your own worldview. You'll also discover news that you wouldn't have otherwise seen from biased mainstream news outlets, providing you with the full picture of what's going on in the world. The app is designed for you to consume conveniently on the go, whether that's reading, watching, or listening to the news. So, burst the bias bubble and get news you can actually trust. Head to san.com/debunked or tap on the link in the description.
When you visit my link, you're not only supporting Debunked, you're finding a trustworthy way to get the news. Let's get back to space.
So, if there is a human-sized hull breach, what happens when the 1 atmosphere conditions and the 0 atmosphere conditions are exposed to one another? The difference in pressure between the two volumes gives rise to what we call a pressure gradient force. And this force drives the air from the high pressure region, the cabin, towards the low pressure region. space. If we had connected two cabins, one with a slightly higher pressure than the other, the flow would continue until the air pressure in both cabins equalised.
In our scenario though, equalisation obviously can't occur. A rush of air from our humble cabin isn't going to pressurise the vacuum of space.
So, what happens then? The air keeps moving out, until either somebody plugs a hole or there's no more air left in the cabin.
So, how quick and or violent is this decompression?
Let's first imagine we're in an average-sized cabin, something like a compartment on the International Space Station, and we have a tiny hole. Would you be sucked through it?
No, and you'd have rather a long time to do something about it.
In fact, a real-life example of this scenario unfolded on the International Space Station. In 2018, the ISS was found to be losing pressure. The leak was traced to the docked Suez MS-09 spacecraft, where a 2mm or 0.08-inch hole, about the width of a matchstick, was discovered. And how did the astronauts handle it? Was anyone pulled dramatically or even noticeably towards the opening? No. Instead, to momentarily stop the leak, astronaut Alexander Gerst is said to have simply plugged the hole with his finger until they could temporarily patch it up using tape and gauze. This comment from NASA Ground Control was recorded on an ISS live feed.
Right now, Alex has got his finger on that hole, and I don't think that's the best remedy for it.
Was he putting himself at risk? Could his finger have been pulled through the hole as the pressure continued trying to reach equilibrium? We can calculate the force at the hole by taking the difference between the inside pressure and the outside pressure values, and then multiplying them by the cross-sectional area of the hole. This would give a pressure difference of about 0.32 newtons, which works out to a force that's roughly equivalent to the weight on Earth of 3/4 of a golf ball. That's hardly going to rip your arm off. According to figures calculated by the NASA Space Flight News Agency,
the leak rate as it stood would have meant they would have run out of air in 18 days.
Which may sound fairly dramatic, but was more a figure to illustrate just how small the leak was. So, if you find a small hole in your spaceship, a good rule of thumb is use your thumb.
But what if the hole isn't thumb-sized? What if the whole door goes? That brings us to Hollywood's favourite method of ejecting undesirables into outer space, the airlock blowout.
There is a moment.
In this scenario, we usually find our hero somehow outwitting or overpowering their respective combatant, whereby said opponent is shoved into an airlock and promptly fired into space by our hero, releasing the outer door. Alternatively, a human-sized hull breach may have occurred, exposing the pressurized cabin to the vacuum of space. In either situation, the room is usually of small to medium size, and the opening is a lot bigger than our previous digit-sized breach. So could this ratio see someone expelled into space faster than a greased puffer pig? A chamber of about 30 meters cubed with a 1 meter square door, when pressurized at roughly 1 atmosphere, would see the pressure drop to 10% in a fraction of a second. The continuous, extreme suction you see in science fiction films is just that, fiction.
And the suction force, from a physics point of view, is sort of a myth.
When the airlock is opened, any air between you and the inner door rushes towards the open hatch, from the high pressure region to the low pressure region, as we described earlier. The resulting force that moves you towards the airlock isn't continuous suction from the vacuum of space. It's ordinary aerodynamic drag. Air particles colliding with your body, exactly like what you would experience on a windy day. Drag force is given by this equation, Without getting too deep into the maths, this shows that the size of the force depends on the velocity of the airflow squared. Space scientists at the University of Leicester, who ran the numbers for the type of airlock scenario you see in the movies, estimated that partway into the airlock, you might be looking at a force of the order of a few hundred newtons. The study concluded
The person would likely get knocked off their feet. However, once they are on the ground, their cross-section will drop to roughly a sixth of when they were upright, and their drag coefficient will also drop, so the force will fall to approximately a tenth, and the person would not get dragged into space.
An important aside here is that they were investigating the same trope as us, and, like the vast majority of sci-fi movies, they're presumably including some sort of artificial gravity. The very idea of being knocked off your feet depends on it.
in more lifelike zero-G conditions, the force would be the same, but you'd be shoved directly towards the opening rather than falling over. What about if you were right at the opening? The airflow here is considerably faster. It can't go faster than about the speed of sound at cabin temperature, but we're still potentially looking at a sufficiently high speed to generate a drag force of the order of several thousand newtons. In this scenario, you would be hit by a force roughly equivalent to several grown adults at Earth's surface, although this push would only last a fraction of a second. As the pressure collapses, it would probably be too much to withstand, even if you have a grip on a solid handhold. If you were tethered, you should be alright. Not the dramatic and sustained megasuction you've seen in the movies though.
So, if the airlock doesn't rise to the task, then how about a large cargo hold with a whopping great set of hydraulic doors?
Where?
In the cargo control area.
Hey Brian, check it out. Meg's poking around the cargo hold. I'm gonna give her a little scare.
Surely this ratio will give us the big blockbuster blowout we're looking for. Bigger volume, bigger problem, right?
The initial rush would indeed be fierce, but the overall story isn't hugely different to our airlock scenario.
When the pressurized space is open to the vacuum, the air rushes out. At the very lip of the doors, the flow is fastest, up to about the speed of sound. Since we have more air and a larger door, we do have a greater mass flow, a greater barrage of air particles battering anything in the line of sight of the opening. But the blast would still only last for a brief moment. Again, if you're right near the lip, you're going to be shoved out. If you're mid-bay, you could be shoved out. The space scientists at Leicester thought about a big door scenario too.
If the size of the door was increased by a factor of 4, so that the hole is 2 meters by 4 meters, the force would increase by a factor of 16. This leads to a force, when the person is flat on the ground, of around 500 newtons, which means they will be dragged out if the coefficient of friction between them and the ground is less than around 0.7, which is reasonable.
Here, in the cargo bay though, the real killer might be debris. A crate, a wrench, or even a loose panel would hit a lot harder than air. If you survive the impact, your spacesuit probably wouldn't. And if your spacesuit is compromised in a depressurized cargo bay, it's game over.
If you enjoyed this content, then please check out one of our other videos on screen now.